Hello everyone, in this video we're going to talk about combinations, and more specifically we'll talk about key combinations. In the last video we talked about permutations. The permutations of n distinct objects is an order arrangement of n distinct objects. The requirement for permutation is that there's no object can be selected more than once and the order of arrangements matters. For the case of combinations or k combinations, this is going to be an order selections of k elements from the set of n distinct objects. And again, no object can be selected more than once, and from the definitions you can see the order of arrangements does not matter. And we count the k combinations by using the following formula. That is, capital C stands for combinations of n, k, where n is the total number of available objects and k is the number of positions. This is equal to n factorial divided by k factorial times n minus k factorial. There's another notation for this going to be this parentheses and then n k. What this means is we want to find the combinations of k elements out of the n distinct objects. Again, I want to note that n is the number of available objects, and k is the number of positions or selections. So let's consider the following example. In this example, I want to talk about the difference between permutations and combinations. So in this example, the setup is that suppose an ice cream shop has 3 flavors. And the 3 flavors are going to be vanilla, V, chocolate, C, and strawberry, denoted at S. And the ice cream is served in 2 scoops, stacked in a cone. So you have the top scoop and the bottom scoop. Now, in the case of permutations, remember the orders matters. The arrangement is going to be vanilla and then chocolate, chocolate then vanilla, vanilla with strawberries, strawberry then vanilla, chocolate with strawberry, and strawberry then chocolate. So there are 6 possibility of arrangements. So in this case, you see that V and then C, that means vanilla is on top and chocolate's flavor is on the bottom. Whereas you have CV, that means chocolate is on top and vanilla is on bottom. So again, permutations, we care about the order of the arrangements, and obviously VC and CV ice cream are visually different. That's why we use permutation for calculate the number of arrangements. However, when we consider combinations, and for combinations the order does not matter. So here we only care about which 2 flavors are chosen for the 2 scoop on the ice cream, not which flavor is on top scoop and which one is in the bottom scoop. Right. So therefore, the choice of vanilla then chocolate and chocolate then vanilla are considered to be the same outcome. Consider to be the same outcome. That means that for combinations in this particular example, we only want to know about the groups of flavors. So that means we only care about groups of flavors. And there's only 3 groups of flavors or 3 combinations of flavors in this particular scenario. That means the first group is going to be between vanilla and chocolate. The second group we consider is vanilla and strawberry. And the third group is going to be chocolate and strawberry. So there's only 3 combinations from this particular scenario. Okay. So most of the time, the number of permutations will be greater than the number of combinations. So hopefully this example illustrates differences between permutations and combinations. Now we're going to move on to another example. In the next example, we'll talk about combinations of playing cards. So for this example, we want to know how many hands of 5 cards can be dealt from a standard deck of 52 cards. So because we're going to get a hand of 5 different cards, we don't care the order of the cards. So this is the example of combinations for n is equal to 52 and k is equal to 5. So we're going to find the arrangement by set up the following formula. So C, which is combinations of 52, 5, this is equal to 52 factorial divided by 5 factorial times 52 minus 5 factorial. This is equal to 52 factorial divided by 5 factorial times 47 factorial. Now you plug this into a calculator and you're going to get to 598,960. So there are 2,598,960 different arrangements of 5 cards can be dealt from a standard deck of 52 cards. Another way that can be very useful to use combinations is identify how many subset from a set of elements. So consider the following example. We want to know how many 6-element subsets are there of the set of A, B, C, D, E, F, G, H, I, and J. So there are 10 different elements in the set. Since we are chosen subset, the order that we choose them does not really matter. So this is the combination scenario. So in this case, n is equal to 10 because there are 10 elements in the set. And k is equal to 6 because you want to find out how many 6-element subsets that we're going to get. And this problem relates to combinations, so the setup is that of C of 10, 6. This is equal to 10 factorial divided by 6 factorial times 10 minus 6 factorial. Well, this is 10 factorial divided by 6 factorial times 4 factorial. And if you plug this into a calculator, you're going to get 210 6-element subsets. Now I'm going to move on to the last example for combinations. And in this example, I want to identify how many bit strings of length 8 contain at least 3 ones and 3 zeros. So you have bit strings of length 8, and the bit string contains only zeros and ones, and the number of ones plus the number of zeros is going to give you the length 8. All right. And the requirement for this again is there's at least 3 ones and 3 zeros. So we consider 3 different scenarios here. The first one is that there should be exactly 3 ones, and the remaining position must be zeros. So when doing these calculations, you get 5 zeros out of the first scenario of exactly 3 ones. The second scenario is that you have exactly 4 ones. And when you have exactly 4 ones, remaining position must be zeros. So there should be 4 zeros from the second scenario. And in the case of exactly 5 ones, again, the remaining position must be zeros as well. So there are 3 zeros from the third scenario. So, and we don't care the order in which the ones and the zero occur. So for the first case, the combination should be C of 8, 3. The second scenario is you have C of 8, 4. And the last scenario, you have C of A, 5. So the question is, why don't we do 5 0 and then 4 0 and 3 0, right? In the case of 5 0, the remaining position must be the 1, so there are 3 ones. In the case of 4 0, the remaining position must be 1s, so there should be 4 ones. And in the case of 3 0, the remaining position must be 1s, so there's 5 ones in the last case. So either approach should give you the same number, and they're going to be like this. So the So we're going to do the calculations for the three cases. For the case of c of a comma 3, you have a factorial divided by 3 factorial times 8 minus 3 factorial is equal to 8 factorial divided by 3 factorial times 5 factorial. This is going to give you 56. For the second scenario of c of 8 comma 4 is equal to a factorial divided by 4 factorial times 8 minus 4 factorial is equal to a factorial divided by 4 factorial times 4 factorial, and this is going to give you 70. And in the last case of c of 8 comma 5, you have a factorial divided by 5 factorial times a minus 5 factorial is equal to a factorial divided by 5 factorial times 3 factorial is also equal to 56. And the number of bit strings of length a is going to be 56 plus 70 plus 56, and is going to be equal to 182 bit strings of length 8. So that's it for the example of combinations. In practice, when you use combinations, when you want to make arrangements to certain objects and you don't care about the order of the arrangement, which is different from permutations where the order of the arrangements really matter. Okay, so that's it for me. In the next video, we're going to talk about something called discrete probability.